Welcome everyone to our seminar. This is a seminar that is jointly organized by the Department of Mechanical Engineering and the UTC Institute of Advanced Systems Engineering. So before I introduce our speaker, I have two announcements to make. The first one is if you are an ME student, of course, please sign in the ME sign-up sheet. If your advisor is affiliated to the Institute of Advanced Systems, we ask you to please take a survey, fill it in, and turn it in at the end of the seminar. That also includes faculty, of course, so faculty, if you could please fill in a survey, we would appreciate it. And with that, the other announcements that I have to make are with respect to safety and the restroom. So we have exits here and two exits in the back of the room. Wow. And restrooms are around the exit here. So with that, it is my pleasure to introduce Professor Daniel Selva from Cornell University. He received a PhD in space systems from MIT in 2012, and he's an assistant professor at the Civil School of Mechanical and Aerospace Engineering there. And he directs the Systems Engineering, Architecture, and Knowledge Laboratory, you can see there in the SIG. And his research interests focus on the application of knowledge engineering, global optimization, and machine learning techniques to systems engineering, design, and architecture, with a strong focus on space systems. Prior to joining MIT, he worked for 4 years in Kourou.
Kourou in French.
In French Guyana, where he was actually an avionics specialist working with the Ariane 5 launch team. He has a dual background in electrical engineering and aeronautical engineering with degrees from the Universitat Politécnica de Catalunya and Supaero in Toulouse in France. And he's also a faculty fellow at the Mario Einaudi Center for International Studies and a member of the AIAA Intelligent Systems Technical Committee. Today, Professor Selva is going to talk to us about his research on cognitive design assistance and mixed-initiative design of complex systems. And with that, please help me introduce our speaker.
Thank you. Thank you, Julian. Can everybody hear me in the back? Is the mic okay? All right. So good afternoon, everybody. I'm really excited to be here and really thankful that Julian invited me to come today. I'm, I guess, between you guys and happy hours, so I'll try to make this as succinct and as entertaining as it can be, although, you know, it's still research. I also have to say my wife really wanted me to say this, that my wife is really a big fan of the women basketball team here. So, you know, she really wanted to come here, but we couldn't make it work. We have an 8-month-old baby, and that creates all sorts of logistics problems. And it also creates a state of perpetual sleep deprivation in myself and my wife. So I apologize in advance if at some point I don't make sense, or if I start speaking Spanish, just raise your hand or something like that. So quick show of hands. How many of you guys are mechanical engineers? Okay. Any systems engineers? One person. Okay, two. Okay, so that's good to know to kind of tune the talk. All right, so today I'm going to be talking a little bit about my research, which is going in this direction of cognitive design assistance. I'm primarily a design automation guy. So I've been doing a lot of work in design optimization, particularly applied to design of complex systems. And to be honest, 99.9% of the time, that's space systems. So I'll be talking a lot about satellites, Earth observation, and things like that. And more recently, we've got a project funded by NSF to look at this kind of stuff, which is, I think, really interesting. And it's this idea of trying to learn from the robotics community and from the intelligent systems community, which, as you might know, is sort of moving away, in a sense, from automation, right, and autonomy, and try to look into more collaboration and these ideas of mixed initiative approaches. So we're trying to see what that looks like for for design. So I'm going to be trying to talk a little bit about that. So just very quickly, an introduction of my lab, and I want to immediately acknowledge that this is mostly the work of my PhD students. So I have 5 of them right now, although 2 of them just joined. So this is primarily the work of 3 of them, Nozomi Hitomi, Nathan Knurr, and Harris Bang. You can see the 3 of them in that picture. And this is a work that is funded by NASA, the National Science Foundation, the MIT Lincoln Labs, MathWorks, and of course, Cornell University. So it seems like it's sort of trendy and fashionable to have a mission or a mission statement. So I try to come up with one for my lab, and this is what it looks like. So primarily what I do is to try to support the design of satellite missions, so next generation satellite missions. And it's typically high-level design, so I'm not designing nuts and bolts and picking batteries and things like that. I'm more at the program planning level kind of design. And while we're doing that, I hope to gain insights and study how design happens in these kind of organizations like NASA, Boeing, and things like that, and try to improve, hopefully, that process. So primarily, we do 3 kinds of activities. So for those of you who are familiar with basic systems modeling, so the oval here, so this is OPM language. So the ovals means functions or processes. The boxes represent means to accomplish those functions. So I'm trying to understand space mission design process. I'm trying to develop tools to help this mission design process, and then hopefully use those tools to actually have impact in the real world and use them to design actual missions. And that's actually something that we're doing right now with NASA as a part of a newly funded mission that's called Tropics for extreme weather monitoring. In terms of how we accomplish those goals, you have here a sample of the tools that I work with every day. So we do a lot of work with global optimization. So I'll be talking a little bit about that, machine learning, visual and data analytics, multi-agent systems, knowledge-based systems, and more recently, human-agent interaction. So let me start with an example. So what kinds of complex systems do I work with? And this, I think, will help me make some of the points that I want to make later in this talk. So we have this 2 pictures that are trying to represent what the architectures look like for the NASA Earth Observing Program today versus what it's going to look like in the future. And that's not according to me. That's according to much smarter people than myself. So the one on the left is representing the current architecture, which is primarily driven by these large multi-instrument platforms. We're talking about maybe 3 to 5 metric tons that are carrying 4, 5, 6, 7 instruments. These instruments can be things like radars, remote sensing, radiometers, spectrometers in different spectral region bands, and things like that. So they're all sharing a common bus. So that means that they draw resources, power, downlink time, and things like that from the same place, right? And to be honest with you, satellites today are pretty dumb in terms of autonomy. I mean, all they're doing is essentially taking pictures, taking images, storing them on board, waiting to be in visibility of the next ground station, and dumping as much data as they can while they're in visibility of the ground station. Most of the planning happens in the ground. There's very little actual autonomy for these missions. There's very little intelligence on board. And there's, of course, reasons for that. Historical reasons and just, the maturity of technologies. But I think that there's consensus in the literature that we're going to move towards something that looks more like what we have in the right-hand side here. So we're going to have these networks of heterogeneous assets. So we're no longer talking about just spacecraft. There's also airborne platforms, aircraft, balloons, UAVs, you name it. All these working together collaboratively, sharing data in real time, making autonomous decisions about what is the next target that we need to be observing at based on data fusion techniques and things like that. So this is, as you can imagine, a much more dynamic architecture, much more connected architecture, and just a completely different design for the satellite mission. So this is sort of a motivation for my work. It's trying to see how we can go from something that looks like this right here. You guys see that? No. From something that looks like this to something that looks like this. So there's a lot of design studies and architecture studies. So how do people do this today? How does NASA design their missions, or other organizations? So there's primarily two different approaches. The one that I come from, I guess, the world that I come from is this quantitative design world, right? So it's design automation, basically. So the panacea, the holy grail would be to have a computer that can design a mission end-to-end, no human intervention whatsoever. You just input, I want to measure soil moisture with this accuracy and this spatial resolution, this temporal resolution and whatnot, and you get the complete design as an output. Of course, we're far from there, but that's sort of the basic approach. And of course, the focus here is on rigor, of course, mathematical rigor, consistency of the answers, exhaustiveness. So we want to explore as many designs as we can, right? So each point here represents a different design, a different mix of instruments and orbits and spacecraft. Consider multiple metrics at the same time. So here we have science, benefit, life cycle cost. We could have other metrics. So this is my world, right? And this is the other half of the design world, which is a qualitative approach, which is things like focusing on methods to do creativity, brainstorming. For those of you who are familiar with that, design thinking, right? Delphi method, trying to reach consensus in a group about decision making. This is an important part of the community that I'm a part of. It's just a new part for me. So I'm trying to, and to be honest with you, there's this wall that is trying to represent almost this chasm that exists between two different communities, right? So I think there's a strong push from NSF to try to make us collaborate more and to try to see if we can come up with stronger research projects together. So today I'm going to be talking a little bit about what I've done in this world, and then I'm going to be sort of peeking through, sort of getting on the wall or something like that and seeing what that world looks like. So let me give you a specific example so that I can talk about in the rest of this presentation. So as part of my PhD and even after that in my postdoc, I did a lot of work for the Earth Science Decadal Survey. So I don't know if you guys are familiar with these kind of decadal surveys, but essentially what it is a multi-year study, really, typically run by the National Research Council, where they bring a bunch of scientists from all these different disciplines in the earth sciences. So that's climate, weather, ecology, geology, you name it. They bring them on in the same room, and they try to make them agree on what is the set of instruments and satellites that they need to satisfy all their needs in terms of satellite-based measurements for the next 10 years. So that's what a decadal survey is. And by the way, there's no engineers in that process. So it's just scientists thinking about what they would like to have. And some scientists are really good. They really have a good engineering sense, but not necessarily all of them, of course. So in this case, I was working on the outcome of the 2007 Decadal Survey for Earth Science, which recommended a set of 17 missions. You have some of the names here. Of course, some of the missions were so far in the future that they had no idea. Some of the technologies were TRL-2, so we really had no details, no information whatsoever to work with that. But so the idea was to try to see if we could come up with a better architecture, given that there were no engineers in the room, right? So a better architecture for that decadal survey that would still satisfy at least most of the requirements or objectives, scientific objectives, and hopefully meet some of the affordability requirements that were there. So this is the formulation or one of the possible formulations that I work with. So we formulated that as a set partitioning problem, for those of you who are familiar with that term from combinatorial optimization, which essentially means that you have a bunch of elements that you want to assign to bins so that the assignment is mutually exclusive and exhaustive. So each element goes into exactly one bin. That's a pure set partitioning problem, and that's what we did here. So we had 13 instruments, which are the elements, and the bins are the spacecraft. So we're assigning the instruments into spacecraft and looking at the space of all possible set partitions, which is actually extremely high. It doesn't look like it, but as usual with combinatorics, the Bell number, which is a number that applies in this case, is about 27 million for 13 instruments. So we're exploring a space of 27 million architectures. We're evaluating one of these architectures, which means computing estimates of science value, life cycle cost, launch risk, programmatic risk. Takes on the order of a few seconds. So it's not something that you can do, with a brute force approach. You need some sort of more intelligent kind of search. What was that? You can do some parallelization across architectures. Unfortunately, you can't do a lot of parallelization in terms of the individual metrics. But yeah. So this is an example of what this, actually this is the reference architecture that they suggested. The blue boxes here are instruments. The black rectangles are the spacecraft. So you see that this architecture has six spacecraft with different numbers of instruments. And then this is just some information that I created here you can think of this as sort of engineering problems. Whatever is red here means that there's going to be some sort of engineering problem related to, say, vibrations, thermal issues, field of view issues, and things like that. So an example of results of the kind of tools that I'm going to be talking about looks something like this. So typically scatter plots. So here again, each diamond is one architecture. I'm just showing the fuzzy Pareto front, so the architectures that are closer to be optimal in the objective way, so closer to the Pareto frontier. You're familiar with that term from multi-objective optimization. So this is science score. This is life cycle cost. I'm not going to go into the details of how this magical science score is calculated. You can go into this paper if you're interested. But I can tell you that it comes from looking at about 1,800 different requirements that they had in this Decadal survey. The color here represents the third and fourth metric, so it's an aggregate of the risk metrics that are less architecturally distinguishing. So you can see some of the traits. Sort of an interesting thing to look at is that this is the reference architecture up here. Sorry, somehow this decided to start working. So you can see that the reference architecture is heavily dominated by these architectures down here by a few $1 billion, actually. And I can explain why that's the case. But probably don't have a lot of time to go there. So the basic idea was these guys here. This is the Destiny mission. This was a mission to study vegetation and ecosystems, which had a synthetic aperture radar and a LiDAR, both very high energy, large instruments, high power instruments. So from the science perspective, it makes a lot of sense to put them together, or at least they thought so. It turns out that from the engineering perspective, that was a nightmare. That was not the way to go. You can save billions of dollars by not doing that, by separating them into different spacecraft. And it also turns out that, at least according to this model, it doesn't make sense from the science perspective either because of the conflicting orbit requirements between these instruments. So anyway, this is just to give you an idea of the flavor, the kinds of problems that I work with, and also the kinds of tools. So this is, when I talk about design tool, this is what I mean. These are kind of tools that allow you to do this sort of design space exploration work. So this was, yes, so I'm going to go into that, but this is primarily heuristic optimization. The results that you saw were based on a very simple genetic algorithm that we implemented. We're now working on much more sophisticated heuristic algorithms, but yeah, it's still in the heuristic world. So the specific challenges related to these design tools that I'm going to be talking about today are essentially related to knowledge. And there's essentially two of them that can be looked at two sides of the same coin, I guess, which is if you think about how knowledge gets transmitted or exchanged between the human and these design tools in the computer, that defines essentially two challenges. The first one is sort of in the direction of the human, from the human to the computer. So how can we represent and use the knowledge that experts have, that these scientists or NASA systems engineers have, in order to guide the search in an efficient and effective way? The other one is sort of in the other direction. So how can the computer, one, sort of explain itself, whatever that means, and two, sort of foster knowledge discovery, sort of help the human learn interesting things about the problem. And the interesting things are things like, what are some design features that maybe the good architectures have in common that bad architectures, according to the model, don't have? So, and this, as you can guess, this is going to go into the data mining world. So this sort of defines the outline for today. So we have this sort of duplex channel for those of you who come from the communications world. So we have the human on one side, the computer on the other side, and we're trying to look at this communication from here to here and this other communication from here to here. And I'm going to be starting with, I guess, this communication from the human to the computer and talking a few minutes about two projects that I work with related to that. One is Vassar, that comes straight out of my dissertation. The second one is knowledge-driven optimization and adaptive operator selection, which is a work of one of my PhD students. And then after that, I'll talk about sort of this other communication, this other direction. And I don't think I'm going to have time to talk about these two things. So I'm going to primarily talk about IFeed, which is work by Harris Bank, one of my PhD students, related to these feature extraction problems. All right, any questions so far? All right, so I'm going to talk about Vassar now. So Vassar is an acronym for Value Assessment of System Architectures Using Rules. But what this really is, you can think about this as an architecture for these value functions, for these objective functions, so that you can incorporate the expert knowledge in a way that leads to scalability and traceability. And I'm going to explain what that means in just a second. So let me just motivate first why we need scalability. Why do we need to express or incorporate a lot of knowledge in this problem that I just described? So this scale right here represents some of the advantages and disadvantages that you need to take into account when you're comparing the two architectures or the two styles, architecture styles that I was mentioning before. So this is sort of multi-instrument mission, so large spacecraft in a sense, compared to this more dedicated mission, single instrument mission, more distributed kind of approach. So it's, in a sense, it's almost like monolithic versus distributed architectures, right? Which is very relevant in other environments as well. And these are some of the issues that you really need to take into account if you want to do a good job with this problem. And some of them, are related to science. The fact that there's synergies between all these instruments. If you put a microwave radiometer together with a radar altimeter, you're going to get a better altimetry measurement because you can correct for the effect of the water vapor in the atmosphere. You get better cross-registration of the data because you can more easily point the instruments at the same point on the surface of the Earth at the same time, right? In theory, it would seem like you have fewer spacecraft, so that should be cheaper, right? Lower bus costs. There's only one spacecraft to design, to build, to test, to operate, right? So it seems like that would lead to cost savings. Actually, models show that that's not the case, really, because it's not a linear dependence on mass size. And then on the other side, we have basically the life of the engineer becomes much easier if you go for this dedicated kind of approach, right? Because then you can really tailor the design of the spacecraft to that specific instrument. Instruments don't have to fight for resources. They can have 100% duty cycles. And then you also have these programmatic sort of advantages that might seem not so important, but they can actually drive decisions made by NASA. Things like time to science. Designing one of these missions can take 5 to 7 years. Designing one of these missions might take 2 or 3 years. So you get science results faster. Risk of schedule slippage, risk of cost overrun. Essentially, everything that's related to risk on cost and schedule gets better when you go for these kind of approaches. So all of this knowledge, basically, needs to somehow go into the evaluation function that I'm using. So if you just want to use your average MATLAB function to do that, it's going to get complicated. I don't know if you guys have experience trying to incorporate a lot of knowledge into just a traditional sort of procedural programming kind of a scripting language. But that gets very nasty very quickly. So what can we do to improve that? And that's where knowledge-based systems come to the rescue. So are you guys familiar with knowledge-based systems, expert systems? That's very old artificial intelligence technology from the 1960s. That's really the beginning. That's how AI started with essentially things like rule-based systems. So modeling the way that experts reason by combining a very high number of really just logical rules, if-then statements. If I'm in this situation, then I should do this. If I see that, then I should do this other thing. So that was successful for a while, which created a lot of excitement in the 1960s with things like MySyn, which was essentially an expert system that could replace medical doctors in diagnosing and diagnosing bacterial infections. AI researchers, unfortunately, quickly saw that this is much too rigid a way of incorporating knowledge in order to be applicable to a wide range of applications, and it's just not the way to go if you want to do general purpose AI. However, it's still a really nice way of and really simple way of incorporating knowledge in a way that leads to easy, simple traceability and simple scalability. So this is basically what I used for my dissertation. So in a rule-based system, you have these rules. As I said, you have a bunch of them. You have a knowledge base that is called a working memory that contains the facts, what you know about the problem at hand, and there's a pattern matching algorithm that essentially solves the problem for you. So we're in a completely different programming paradigm here. It's no longer the procedural approach, do this, and then do this. It's an approach that's called declarative, for those of you who are familiar with that, which essentially means that you're just sort of constraining the problem in a sense, or expressing what you want to accomplish, but not necessarily how. And then this inference algorithm takes care of that. So just two examples of how I actually use that to encode knowledge. So this is a rule that encodes, that represents disaggregation data processing scheme. And it's basically telling you that if you have two data sets for soil moisture, one with high spatial resolution, low accuracy, that comes from a radar. One with low spatial resolution and high accuracy, that comes from a radiometer. Then you can do a data processing that's called a disaggregation scheme that will create a third data product that will have essentially high spatial resolution and high accuracy. So that's one example of one rule. Another rule would be something that's very easy to understand, which is that if you put two instruments and one of them is active and one of them is passive, and the two use the same frequency, you're going to have interference. So that's not a good thing, right? So that's just two examples of how you use these rules to express knowledge. And this is what Bachelor looks like. It's basically, you can think about it as a software architecture for these value functions to evaluate space system architecture. So you have the architecture right here, the mission facts that you create, that's the instrument facts, and you create measurements facts. So this would be the spacecraft, this would be the remote sensing instrument, radar, and so forth. This would be the actual measurements, raw measurements. And then we go through this process, the measurement chain here, where you're essentially applying different sort of data processing schemes, different synergy rules, and so forth. And at the end, you get the final measurement set that you compare against your requirements and determine how satisfied you are at the sub-objective level. So that's at the level of those 1,800 different requirements that we have. And then, of course, you're in a hyperdimensional objective space. You can't make any decisions there, so you have to aggregate so that you go into either one or a few metrics where you can more easily make reasonable decisions. So I'm not going to go into the details of the Bachelor architecture, but if you're interested, you have here the paper. This won the Conference Best Paper Award at IEEE Aerospace in 2013. So something that's nice and related to what's coming in the rest of the talk is when you have this knowledge-based approach to evaluation, you can start doing automatic generation of explanations. So, something that you realize very quickly is that optimization algorithms have this tendency to find flaws with your models, right? So, they just find the path to optimality, and typically optimality is constrained by something, and that's either a real constraint or a fake constraint introduced by your model, right? So being able to actually ask the tool, why do you get a science score of 0.48, is actually an extremely useful thing to have. And so that having this knowledge-based architecture actually allows to generate explanations immediately just from basically the trace of the rules that get executed. So again, I can't go into too much detail, but the idea is facilitating this automatic generation of explanations. So in this case, I can automatically explain that this architecture right here is better than the reference architecture because it has higher science and lower cost. It has higher science because this one partially misses this or this other sub-objective, and it has lower cost because you have to put a LiDAR at 600 kilometers, which is extremely expensive power-wise, and you also have savings in terms of launch cost. So this is very useful information for them. Yeah, so no. So this was essentially unranked, raw, text-based explanation. Yeah, and so I'm going to... Yes, unfortunately, that's the problem, right? So, so some of the directions for future work is, once you have all these explanations, there might be even too much information. How do you condense those explanations into a smaller set that is easier to understand and also self-consistent if possible, right? But no, you're right that this was not taken into account here. All right, so Bachelor, as I explained, is a way to generate explanations and incorporate knowledge, right, into evaluation. So that's one step in design, right, evaluating the design. The other, or another step, is searching. So what I'm going to be talking about now is how do you incorporate this knowledge into the search aspect of this. So not the evaluation, so computing output as a function of inputs, but rather the search, which essentially means what is the next design that I should be looking into. So how do I guide the search with knowledge, basically? And I'm going to be talking about something called knowledge-driven optimization, and in particular, adaptive operator selection. So first of all, to sort of set the scope or the context of this, and related to the previous question, so this is very hard to do with traditional OR kind of optimization techniques like linear programming, gradient-based, and things like that. So the world that this was done in is basically evolutionary algorithms. And it doesn't really have to be evolutionary. Any kind of heuristic or meta-heuristic would apply. So if you can define your search as an iterative search where you have one or more operators that move you in that search space, you can apply everything that I'm going to say today. So, but that being said, as everything was done with evolutionary algorithms, so that's a very popular way, especially in industry, to solve complex problems. That's because they're very flexible tools, right? And that have provided actual results. They actually work. People don't really understand why, but they actually work, right? So things like genetic algorithms, NSGA2, Epsilon MOEA, so those are some of the things that we were working with. And the basic idea is that you have an initial population of designs or architectures, and then you have a number of operators. So in the genetic case, typically you have a crossover operator that mimics sexual reproduction, and then a mutation operator that sort of incorporates small random changes in your architectures to foster exploration, right, as opposed to exploitation. So something that we've done a lot of work, in particular my student Nozomi Hitomi has done a lot of work in, is this idea of hyperheuristics, or some people call this self-organizing optimization. So the fundamental idea is that we want to make optimization more robust. So we don't have to worry about choosing different flavors of crossover operators, tuning crossover or other parameters in the GA. We want to be able to just plug in the problem and solve it in an efficient way, and want to be able to reuse the same algorithm for a wide range of problems. So that's where hyperheuristics become useful. So the basic idea is that you have a pool of operators, again, and that could be domain-independent operators like crossover and mutation, or, spoiler alert for what's coming, it could also be domain-specific operators. Operators that actually encode some of the knowledge that you have about the problem. And then once you have that, what you need is basically just a way to measure the performance of those operators, and then some way of assigning resources proportionally to that performance, right? So that's basically the credit assignment part of this and the operator selection part of this. So the credit assignment is measuring the performance, so the credit that an operator receives at time t, this is the basic idea. If you're in the single objective world, you can just look at the fitness function of the offspring that you have generated from the crossover operator, for instance, and compare that to the parent solution. So essentially, this is looking at, am I improving the fitness by doing this move in the space, yes or no? In the multiple objective case, it gets a little bit more complicated because there's no objective way of combining objectives, of course. No pun intended, or sorry for the redundant use of the word objective. And then in the operator selection aspect of this, if you have some way of measuring the credits, you just need a way of assigning resources, so designs, to the operators in a proportional way. So if an operator is working very well, I'm going to give it a lot of designs. If an operator is not working well at all, I'm not going to give it any designs. So that's what, it's essentially a controls problem in a sense, right? So you can see here, so This is a very basic operator selection strategy that's called probability matching that basically tries to, it's a stochastic approach where the probability of picking an operator is essentially proportional to the credits, but bounded by a minimum probability so that you foster a little bit exploration. So, yeah, it's similar. So if you're familiar with multi-arm bandit approaches, so it's similar to trying to pick the arm that would maximize the expected reward, but without being that greedy. You are a little bit less greedy by introducing this minimum probability. That's a great question. And so what we have seen is that when you put too many operators, it takes too long for the hyperheuristic to be able to catch up with a regular or a state-of-the-art evolutionary algorithm. So typically we're talking about 5, 6, on the order of 5 to 10 operators. If you go to say 20 or 30, then it gets complicated computationally. Yeah. So I'm not going to go into a lot of mathematical detail, but just to show you how this works. This is basically showing 3 different hyperheuristics, and they're different in the way that they assign credits and in the way that they do the operator selection aspect of this. And you can see the credit history of all these different operators. So the different color lines here are different operators. So these are primarily different sorts of crossover and mutation, SBX, simplex crossover, PCX, SPX. So the different operators that are typically used with real continuous optimization problems. And you can see how very quickly the hyperheuristic learns or identifies that SPX is actually the best operator in this case. It's interesting to see that if you change the hyperheuristic, you go from a 1-operator-based search to a 2-operator-based search. And in this case, it's SBX and PCX. And you can see how one of them is more effective at the beginning of the search, and the other one is more effective at the end of the search. And that has to do with the characteristics. One of them is fosters exploitation more than exploration, basically, in the search. So we've actually done a lot of work with these and have shown that you can outperform state-of-the-art evolutionary algorithms by incorporating hyperheuristics if you're looking at a wide range of problems, right? If you're just looking at one problem and you do some experiments and find what's the best operator for that problem, then of course that's the best operator for that problem by default, right? But when you're looking at a set of benchmarking problems, actually 26 of them, on the average, hyperheuristics outperform. So how am I doing in time? Oh, wow, okay. So here's the idea. We have these hyperheuristics where you can have a pool of operators, right? So far, what I've shown is domain-independent operators, a bunch of different crossovers. But why not incorporate knowledge into this pool of operators in the actual operators? So some of these operators will be essentially knowledge-driven. So examples of those would be an operator that knows that 2 instruments are synergistic. That doesn't mean that they should be together all the time, right? But there's a positive relationship there. So it's going to try to not in a deterministic way, but in a slightly stochastic way, it's going to try to put them together, essentially, on the same spacecraft. Or something that tries to avoid putting more than one high-energy instrument on the same spacecraft. So those are just two examples. So what's interesting about that is that if you just try to do that, brute force, so incorporate a few operators into the pool, it actually doesn't work. And the reason for that is because it overexploits the knowledge that you incorporate in the operators. So it works a little bit from the convergence of from the perspective of convergence, but you lose in diversity. And so if you're familiar with multi-objective optimization, diversity is a big deal, right? When you find your operator frontier, you want to have a operator frontier that's populated all along, right? You don't want to have all of your solutions in a very narrow area of your operator frontier. That's a diversity aspect, right? So if you just try and put the operators, it doesn't quite work. And this is actually where hyperheuristics help a lot. And when we did the test of adding the hyperheuristics so that you get this adaptive operator selection, then you can see the effects and you can see the improvements. And you can see that it actually statistically significantly outperforms the absence of knowledge. So you can see here how the credits assigned changed. So these are the examples of the knowledge-driven operators, and you can see sort of the final outcome here. So this is epsilon MOEA, which is a state-of-the-art evolutionary algorithm. That's the red dots. And the circles, the blue circles, are the hyperheuristic that we created. And you can see that it's farther towards the right. So that's, better science at lower cost, right? So that was the second part of the story. Still in this direction of incorporating knowledge into the optimization. So now I want to spend a few minutes at least talking about the other direction of communication, which is this direction, right? So how do we foster knowledge discovery? And for that, I'm going to be talking about a method and a set of tools that my student Harris Bank has been developing and that we've called IFeed, for interactive feature extraction for engineering design. And here is where I'm going to be talking a little bit about data mining, although it's fairly unsophisticated. It's very simple data mining approaches. So the main idea is very simple. If you have worked with these tools before, or if you ask anybody who's worked with these tools before, they're going to tell you something that sounds like this. Yeah, these tools are great, but I'm never just going to pick whatever solution it gives me, right? It's not the way that you use these tools. You use these tools to gain knowledge, to gain information, to gain insights. So that's an interesting thing, but that's not what the tool is doing at all, right? The tool is just optimizing. So how can we make tools actually explicitly help you in this knowledge discovery process? So that's the basic idea. And by the way, so the kinds of insights that I'm after here are things like this question. So what things do architectures have in common in a particular region of the space? So here. Or it seems like clearly there's 3 clusters. So what puts me in this cluster, right? In terms of design decisions that I can control. So this is just an example that comes from a guidance, navigation, and control architecture problem for NASA, for the Constellation project. So this was the number of 9s in reliability of GNC architecture versus mass. So in this case, it was just essentially, your redundancy level, these clusters, right? So the minimum between the number of sensors and the number of computers, which is essentially the size of your minimum cut set, if you're familiar with that. Yeah. All right, so we want to find these driving features in a way that is not fully automatic, and I'm going to try to explain why, but at least semi-automated. And hopefully the idea is to try to maximize this knowledge discovery, right? So just to give you an idea of what we're after in this example, which is the one that I'm going to be using, these are an example of driving features. So if you look at these blue designs compared to the black designs, it's things like at least 3 orbits are populated with at least 1 spacecraft. No more than 1 large instrument is put on the same spacecraft. And these 3 instruments are always on the same orbit. So this is, I guess if you put it in logic, it would be a conjunction of 3 disjunctive forms. So the way that we do this, it's actually extremely simple and unsophisticated. We use a technique from unsupervised machine learning that's called association rule mining. So the fundamental idea is just simply to try to find these design features that are more common at the intersection where so let's explain it with this Venn diagram because it's going to be easier. So U here is all of my designs. F here is all the designs that have the feature. C here is all the good designs, for instance, the ones that are on the Pareto front. So in general, there is some intersection here, right? So I want to find the features for which this intersection is as close as possible to F and C. So it means that F intersection C is as close to F and or C as possible. And that's essentially what these confidence metrics are looking into. And then I want to be correcting for statistical significance. So I don't want to make these decisions based on very few points. So that's where support and lift can help you with. So here's the thing, though. If I do that, if I use a priori or other basic algorithms to explore the entire feature set to find features that have high confidence and high lift, it's, we have a dimensionality problem. It's too big. We can't do it. Too many features. Just to give you a motivating example, a lot of these problems are binary, right? So you're in a binary space. There's 2 to the n different architectures, but there's actually 3 to the n different features, right? Because each position can either be 0 or 1 or unspecified. So the feature space is larger than the design space. So what we do is incorporate the human in the loop so that we can incorporate the expert knowledge about what we think are promising classes of features, and then use the machine to sort of explore those subset of classes of features in a more exhaustive way. So this is the IFeed methodology. We start by formulating a set of candidate driving features. We then select a region of interest in the trace space, so that's defining the C, the class label. And then we do the data mining. And then we are also going to try to explain that to the user in a human understandable way. So for that, association rules are very nice because they're among the most human understandable machine learning tools. And classification trees are also very nice for that because they're also very easy to interpret usually. So we do that, and we sort of keep iterating. And the purpose of the iteration here is to strive towards generalization. We want ever more compact features and ever more higher predictive power features. And that's the search that we're trying to do in this feature space. So these are just some examples of the feature classes that we're looking at. So present, so that means is this instrument present in any orbit, yes or no? Absent, so that's obviously the opposite. Is this instrument in this orbit, yes or no? Are these 2 instruments together in any orbit or in this particular orbit, yes or no? Is this orbit empty, yes or no? So typically these are predicate functions, so there's binary features. So the thing that we do now is to select a region of interest, and I can show you so how does this work? Video here. Let's see. So you can see the GUI that Kerry's created. So I don't know if you can read this, probably not, but he's basically creating a new filter. So it's looking at a specific orbit, which is an afternoon orbit at 800 kilometers, and a specific instrument. And you can see how the instruments that have that feature get highlighted. So this allows you to see what kinds of features you might be interested in, and also it allows you to find the region of interest in an automated way. The next step, of course, is the data mining step. So let's see if I can run this one. So we run the association rules. So you see how the user is now defining the region of interest. That's the blue area. You click on running the data mining, and what you get, you're going to see is a bunch of bar plots. So each bar here represents one feature. So I don't know if you can read that, but this is saying, for instance, together in orbit, so these 3 instruments are together in that specific orbit, and they're sorted, as you can see, by lift. So this is one of the important measures that is used in association rule mining. And very importantly, we have this graphical representation so that people that are not familiar with machine learning can understand, what lift and confidence mean. So you can see here the Venn diagram that I was talking about. So in this case, it looks like 440. Out of the 2637 designs, there's 500, I can't see this very well, but 500 that have the feature, 400 and something that are the blue region, and the intersection is pretty big, right? So it's a pretty good feature in terms of predictive power. So what we do then is build a classification tree. So I don't know if you guys are familiar with that technique, but it's basically a recursive selection of the feature that gives you highest information gain. So an information gain being defined as essentially this formula here. So how much do I reduce randomness, basically, or variation? It's not really, we should think about more in terms of variation when I make a split based on that feature. And when you do that, you can not only have a flat list of features, but have this structure that's sort of nice, this hierarchical structure. So if you go to the classification tree, you can see what it looks like. So It's actually a foldable classification tree, so in real time you can decide to have more or less depth, and you can also see in real time the features that get selected in each of the branches, so it can help you a little bit understand what the structure of the feature space is. So I know that I should stop very quickly, but I just want to use 2 minutes to talk a little bit about the vision. So I talked a lot about design optimization, visual and data analytics, how we can use this to improve knowledge communication, right? But really and again, the emphasis, I guess, in the community has been a lot in this making tools smarter and making them more adaptive. And, I've shown some work that I've done in that area. But I think that the vision or the promising direction to go into, or at least the one that got me NSF funding, let's put it that way, is to try to think of these tools as intelligent agents. And then once you've made that connection, you can sort of learn from the intelligent systems community, the robotics people, right? The robotics people, they work in human-robot interaction, human-robot collaboration, right? They're doing a lot of work, learning a lot of interesting stuff. Does that body of knowledge apply to design? Probably, to some extent. I do think that design is the kind of unstructured task that would benefit from moving away from autonomy and looking into these more collaborative approaches. So this is the idea. So design is a highly unstructured task, and so maybe we can do something like mixed initiative design. And sorry for I couldn't help myself to use this chess-based nomenclature here for, I guess, check and checkmate, and we're not. So the idea is that today we're either here or here in design, right? Either 100% manual, 100% autonomous. Can we go somewhere closer to a more balanced functional allocation? So I don't have a lot of time to talk about this, but what is mixed initiative design? So the idea is to move away from clearly defined master-slave roles and to look into things like having shared plans. So both the human and this cognitive design assistant have a shared plan of what they want to accomplish, how to search this design space, what the goals are. They can dynamically change roles. So it's no longer the human as the creative part of this and the computer as the analyst. They can critique each other's designs and augment each other. Things like shared attention. So they're both paying attention on the same thing at the same time. And then, of course, things like trust become important, right? So what does trust look like in design? And something that my NSF work is looking at with Guy Hoffman from Cornell is embodied interaction. So is a visual interface even the right way to go for this? Or would it make a difference if we have actually a robot that's sort of your design companion in a way? So anyway, that's the vision that I have. I have a couple of cool pictures here of cognitive design assistants. I'm right now starting the development of the first cognitive design assistant for NASA to design Earth observing missions. So we'll see how that looks like, what that looks like. And I'm going to stop here before you ask me to do that. And I'll be happy to take any questions. Or we can just go to happy hour. I mean. Mm-hmm.
And after you follow your presentation related structure. Mm-hmm. And I wonder, can you point out at least one feature which was on the left side, empathy, creativity, which will be on your right side?
Yeah, absolutely. And to a certain extent, there's creativity in just how you pick those features, for instance, in IFeed, right? But so right now, for instance, I'm collaborating with a person at Cornell who's from the Design and Environmental Analysis Department. She's more of a classical human factors, human-computer interaction person. And so what she helped me discover is that the way that you design these GUIs is extremely important. So we do experiments with human subjects to see what kinds of interfaces work better, or even algorithms. Is a classification tree the way to go, or is it something better, right? So we put these tools in Amazon Turk and have people actually do, these experiments to try to see what knowledge they gain, and we compare the outcomes and see what works best. So something that I discovered from the left side, I would say, is that if your GUI is not well designed and a good amount of aesthetics go into that, you can think that you're discovering or seeing an effect, but that's actually just your crappy GUI, if you know what I mean. So there's statics aspects that go into understanding this communication between the human and the tool that are very important if you don't want to reach incorrect conclusions. So I don't know if that's sort of related to what you're going for, or?
Yes, but you mentioned a very important aspect. So before you start your modeling, you need to define your variables, your constraints.
Mm-hmm.
And it is the most important, I think, during the modeling. So this is the beauty, because I can see the depth of your thinking.
Uh-huh.
So if you can add in the future your structure, how to organize, because for me it was like a black box.
Oh, I see. So I guess you were talking more about, say, for the Earth Science Decadal Survey, how you go from the ill-posed problem formulation to the set partitioning problem. Yeah. So that's a good point. And to be honest with you, that was not a straight line that led me into set partitioning, right? So we tried a lot of different formulations. And actually, set partitioning is just one view. My take on this is that there's no model that can give you the full answer. So if you want to get insights, you have to have multiple formulations at the same time. So we looked at this from the perspective of, set partitioning, sure, but also how do you plan the missions, when should we launch the missions, which instruments we should even be considering as candidate instruments in the first place. We considered many different metrics originally and down-selected to just these 4 for this particular case. But the big picture, the actual decision can only be made when you've looked at all these things simultaneously, right? So I guess it's always an iterative process, and that's why I think that looking at human-computer interaction and collaboration makes more sense than just automation. Mm-hmm. Yeah.
So there are many different supervised machine algorithms.
Mm-hmm.
How do you choose that?
Yeah, that's a good question. So as I said, we were trying to go for something that is humanly understandable and as simple as possible. Just from looking at the literature, it seems like association rules and classification trees were 2 of the most commonly cited humanly understandable machine learning models.
You